Hello, this is Nick of Time. Welcome to this 9th talk in the series about time. We're currently talking about the twin paradox of special relativity. Remember that special relativity says that all inertial frames are equally good at describing physical reality. And the key construct is relative velocity. Relative to velocity to each and any inertial frame. That's a sharp contrast to the preferred frame view. An example of a preferred frame is Lorentz ether theory that we talked about earlier. In a preferred frame theory, you have a single preferred frame, and the key construct is absolute velocity with respect to that single frame. Now, when we talk about the twin paradox, often it's talked about in terms that really simulate a preferred frame, even though the twin paradox is about special relativity. So, in this picture, we see the start frame or the base frame, and we view everything from the perspective of that start frame. So we're kind of led to think in terms of a preferred frame, where the start frame is representing the preferred frame or simulating the preferred frame. And even when we talk about the twins, one is usually labeled as the stationary twin and the other one in the astronaut suit is talked about as the traveling twin. Whereas if you had a picture of two spaceships passing each other in deep space, you'd have no criterion, especially within special relativity, of calling one stationary and the other traveling. And before we talked about an acceleration-less scenario, and there'd be no criterion for distinguishing the base frame from, say, a traveling frame. So that's what we have to be careful about, is making sure that when we're talking about the twin paradox, we understand it in terms of the model that's being used. Because often, the relativist will try to reconcile the twin paradox claim using a preferred frame theory, but doing it subtly and not explicitly. And perhaps unconsciously and tacitly. Here's another example, and this is even clearer because the main frame, the base frame, the start frame, is the Earth frame, and that, would seem to have a singular quality, and that's when you picture it mentally, you're thinking about that as some special frame with special properties, and then a traveling frame is traveling with respect to that single frame. So we need to be careful about that. Okay, we're examining special relativities being interpreted. Special relativity time dilation is being interpreted as describing physical differences in clock rates. Okay, again, the relativity principle and special relativity replace the preferred frame model, which is the true physics model, with all frames equal math modeling. Okay, remember we have already shown several QED arguments why interpreting special relativity's time dilation as describing physical differences in clock rates, and that leads to contradictions. Another way of saying it is interpreting special relativity's time dilation as describing physical differences in proper time accumulation rates leads to contradictions. Proper time just means the difference that a clock shows or has accumulated between two well-defined events. Events where the clock is present. So that's what proper time is. When I say QED, that's from the Latin, meaning quod est demonstrandum, and that simply means that which has been shown, and it's come to mean an argument that uses valid math steps and or logic steps. So when we say we have already shown several rock-solid arguments by interpreting special relativity time dilation as describing physical differences in clock rates leads to contradictions. Well, special relativity's twin paradox claim looks okay if you just use a single scenario's start frame and view everything from that perspective. Because that start frame is used to simulate the preferred frame. But you also need to accept the relativist's excuse for not consistently applying special relativity to both twins. We discussed that in our previous talk. It's not valid, it's actually not valid to just focus on one twin view. You need to be consistent and focus on both. And when you do that, you see there's a contradiction, but we will give the relativists a break and ignore that major problem and take a look at another problem just to show how deeply flawed the physical interpretation of time dilation and special relativity is. And this is pretty simple and straightforward. So we look at this additional twin paradox problem. If we have, we're going to now look at just two scenarios instead of just one scenario. We'll see where the conflict comes in. The conflict comes in because if you're trying to have the start frame represent the single preferred frame, and then you use two scenarios, then you have a conflict, because now you have two preferred frames at once. Two frames that are different frames, quite different frames, and they're both supposed to be the single preferred frame. That obviously leads to contradictions. And it's best shown when you're dealing with proper time. Okay, in the first scenario we have frame A as the start frame, and frame B is the B twins or B clock's outbound frame. So the twin paradox claim is that clock B1 is slower than clock A1. But the problem comes in if one adds a second scenario where we switch the roles of twin A and twin B, and switch the roles of frame A and frame B. In the second scenario, we have frame B is the start frame, and frame A is A's outbound frame. So the twin paradox claim is that the A2 clock is slower than the B2 clock. Now to the third point. However, we know from empirical evidence that all clocks at rest in the same frame have the same rate and accumulate proper time at the same rate, other things being equal, like equal gravitational potential. But the first bullet and the second bullet above cannot be consistent with this third bullet. Therefore, we show again that the physical interpretation of the twin paradoxes, special relativity's time dilation leads to a contradiction. We'll show that now in math symbols. In other words and symbols, from the two scenarios, we have the following results. A1's clock rate was greater than B1's clock rate, and B2's clock rate was greater than A2's clock rate. But, given that, we cannot also have the A clocks having the same rate and the B clocks having the same rate, which is required by the empirical evidence. QED. You have clear logic showing a contradiction in that interpretation of special relativity's time dilation equation. So, I thank you again for joining us for this 9th talk, and hope to see you again next time when we'll continue to talk about twin paradox. Because the twin paradox is all about proper time, and proper time is an inherently excellent physical construct. It's observer independent, and that accumulates. So any changes are preserved because they're accumulated. And it gives us great insight into the issues that we've been talking about. So hope to see you next time.